Welcome everybody to our seminar. So for those who are here for the first time, this is the seminar organized by the Network on Electromagnetic Effects in Strongly Interacting Matter. If you want to be subscribed to our list, to follow our activities, just send me an email after the seminar. Today we have the pleasure to have Norberto Scoccolla talking to us. He's part of our network and he will teach us some of his work about regularization schemes in effective models, including magnetic fields. So let me first briefly introduce Norberto. Norberto got his PhD from Instituto Balseiro, Argentina in 1985. He did several postdocs at CEA, Saclay in France, Regensburg, Germany, Niels Bohr Institute in Denmark, and since 1993, he has a permanent position at Comisión Nacional de Energía Atómica in Argentina. So he's currently doing a sabbatical at University of Valencia in Spain. So now it's 7 p.m. for him. He's delaying his dinner to talk to us. So thank you again, Norberto. So he's mainly interested in nuclear physics, in hadron physics. As most of you or all of you know, he's a super expert in effective models. He has worked with SPERM model, NJL, RGNC, QCD, and some others. And recently, or not so recently, he's focusing a lot of his work in strong magnetic fields, effects in the QCD phase diagram, hadron properties, and he will talk to us about this recent work. And thank you, Norberto, again. Microphone is yours.
Anna, thank you very much. Thank you for the introduction. Also, thank you for setting up this network, which I find very useful. I think I'm very happy that we have these talks here. So following your suggestion, I will talk about a couple of technical points, which, however, I think are important to understand the physics of some papers that have been published in the literature. And this has to do with the regularization methods used in the presence of the electromagnetic fields within effective models, in particular within the Nambu-Jona-Lasinio model. And the other point I would like to discuss is the treatment of the charge mesons. So I will start my seminar with a brief mention of the Nambu-Jona-Lasinio model and the ways that are used to regularize it in the absence of the external field. Then I will discuss what has been used to regularize or how to extend these regularizations when an external magnetic field is present. And I will show some results which are based on a work together with Sidney Avantini, Ricardo Farias, and William Tavares. In the second part of the talk, I will discuss how the charged mesons should be treated. And this is based in a series of works together with Maximo Coppola, Daniel Gomez, Thiago Nogueira. And then I will come to some summary and outlook. So the Nambu-Jona-Lasinio model at the zero magnetic field, I think most of you are very familiar with this. It has 3 parts with small current quark mass. And then there is a local quark-quark interaction, which is currently invariant. So if G is not small enough, then you cannot use perturbation theory to treat this. Then you have to use for the operator the mean field approximation, where some diagrams are sum up to all orders. So this is schematically what you do at the mean field, which is equivalent to solving this equation, where this is the effective mass of the quark, this is the current quark, which was in Lagrangian, this is the coupling constant here, and this is the quark condensate. of course, quark condensate can be calculated from the quark propagator, and this you notice that here you have the dress quark. So in this loop, you have the dress quark running. So this is translational invariance. So this coordinate space. Therefore, you can use Fourier transform to diagonalize it. This is the symbol here. This is a shorthand notation for the integral over 4p. Okay? Then you replace this into this and this into this, and you get the gap equation. Of course, this integral here is divergent, so you have to specify some way to regularize it, and this is also part of the model. So the regularization method, in a way, also defines the model, not only the parameters, but also the way that you are going to regularize this integral. So this is at mean field level. When you go beyond mean field level to treat the mesonic excitations, usually people use the RPA approximation in which one sums over a series of the diagrams of this form. And this gives rise to this equation. This is the inverse meson propagator, which has a part which is the delta function coming from this diagram, and a contribution from the meson polarization loop. This is written in coordinate space. So here, this is the propagator that I have written in the previous transparency. And this here is here. And these are Dirac flavor operators related with the quark meson vertex. For example, for the case of the pion, this would be I gamma 5 tau. So using the form I've shown in the previous transparency and performing the Fourier transform, you get this diagonal form for the meson loop polarization. Again, this integral is divergent, and again, you have to specify some way to regularize. Once you obtain a regularized form of this meson polarization loop, then you can come to this equation and find, for example, the meson mass. Notice that I'm using Euclidean space coordinates, so that's why I have a minus here. Okay. So, which are the regularization methods that have been used in the literature? Well, one possibility is to use the so-called covariant regularization, in which you replace the integral over form momentum by an integral over the angles in four dimensions, and what you put is the cutoff in the modulus of the form momentum. Okay, so you cut in a covariant way in the sense that you cut the modulus of the form momentum. Then there is this 3D cutoff, which was also very much used, in which you perform the integral over P4 over the whole space between minus infinity or infinity, and you put a cutoff in the modulus of the stream momentum. Another still alternative way to proceed is to use the proper time regularization, in which you replace this 1 over p squared plus m squared by this integral. Of course, if tau is positive, then you can perform this integral and you come back to this. But in the limit tau going to 0, this is divergent. Therefore, what you do is to put the cutoff in the lower part of the integral so that this is finite. So this is the way that you introduce the cutoff here. And finally, there is also the Pauli-Villars regularization, in which you replace this integral of the function that you want to regularize by the sum of several terms. The first one corresponds to original f. So that's why I have 1, 0 here. So 1, so this is 1, this is 0, you recover this. But then you add some counter terms in order to cancel the divergences. And usually people add 2 counter terms, so this runs up to n equal 2, and the coefficients are given by this. With this, you are sure that your integrals are convergent. There are other methods also used in the literature, which, for example, dimensional regularization, to add an extra cutoff in the infrared, and so on. But these are the 4 that I would refer to, which are the most, the ones that have been mostly used. So then the model has 3 parameters: the current quark mass, the coupling constant, and the cutoff. And these parameters are chosen such that one reproduces f pi, m pi, and gives some reasonable value for the quark condensate. Of course, these two are very well known experimentally. This is not so well known. These are typical values taken from QCD sample, for example, or lattice QCD. So you have some uncertainty here. So you have some, usually you have some range of parameterization, possible physical parameterizations. So at B equals 0, the properties, for example, of the pion does not depend, do not depend much on the regularization choice. So people have used different regularization and results are more or less similar. However, I have to stress that proper time tends to give rather small values of the quark mass of around 200 MeV, while 3D allows for larger values ranging from 350 to 400 MeV. And the other two, polyvillars and 4D, are in between. So they give you values of around 300 MeV. So it depends a bit. For example, if you want to use this model, I'm sorry? If you want to use this model, for example, when to introduce vector mesons or to describe baryons, then you better use something that has larger quark mass. Anyway, so what to do when you now, introduce the magnetic field? So to do that, you will replace the derivative by a covariant derivative, and you have to choose some gauge for a vector field. So for a magnetic field along the third axis, which is the standard convention, in the lambda gauge, this is the form of the vector potential. So as well known, the motion in two planes, so the plane perpendicular to the third axis, to the magnetic field axis, the motion is quantized, and then you get the famous Landau levels. And there is then a standard prescription to introduce, to start from the B equals 0 case and then introduce by magnetic field by, for example, making this replacement, as, for example, you can see in the paper by Eduardo and Anna. So basically, you replace the 4 momentum square by the sum over the fourth component square, the third component square, plus the kinetic energy that comes from the motion in the 1-2 plane, which is quantized. This K labels the Landau levels, and this BF is the modulus of the quark charge and the magnetic field. I will also introduce the sign I will use later. And then for this 4 integral and the sum of spin, you replace by some factor here, which has to do with the sum degeneracy, and the integral over P4, integral over P3, and instead of integrating over P1 and P2, you sum over Landau levels. So you do this replacement in the Nambu-Jona-Lasinio gap equation, and you get something like this. So of course this is divergent, and again you have to regularize it. I'm sorry. Oh. No. So this is the obvious extension of the 3D cutoff method. What you do is to perform the integral over P4 and demand, if you like, that the kinetic energy is smaller than the cutoff lambda. So the sum of P3 squared plus 2 kbf, this has to be smaller than the cutoff lambda. So basically this amounts to replace this sum and integral by a sum over A up to a certain maximum lambda level, which is given by lambda squared divided by 2f, integer part, and an integral between lambda minus lambda prime and lambda prime of P3, where lambda prime is lambda squared minus 2k bf. So you do that, and then you solve the gap equation for certain parameters. And this is what you get. So you get very strong oscillations. These oscillations are not physical. They has come from the fact that you have an integer part here. So you have a jump each time that the new Landau level enters. So, oops, I'm sorry. So for example, the first jump occurs when the magnetic field is lambda squared divided by 2 QD. So in this region, you are summing up to n equal to 0. In this region, you are summing up to n equal to 1 for the d quark. In this region, you are summing up to 2 for the d quark and to 1 to the u quark and so on. So each time that the new level enters, you get this jumps. So of course, people realized about this many years ago. So one possibility to solve this problem is to introduce some smooth function, so some regulator. So if you take here a Heaviside function, you recover this. So instead of using a Heaviside function, you use a smooth function. So for example, this is the function that was used by these people, which is kind of with Saxon, with some factor here. And this is the result you get. So obviously the oscillations are less important, but they are still there. Mm-hmm. What I think is important is to realize that these oscillations have nothing to do with the Van Alphen-de Haas oscillations, are often confused with Van Alphen-de Haas oscillations, although they have nothing to do with them. Van Alphen-de Haas oscillations appear when you are a finite chemical potential and your chemical potential is increasing, and each time that it reaches a certain value, a new Landau level enters. And this makes these oscillations. So, and these are really physical oscillations. These oscillations are just due to the form factor regularization procedure.
Norberto?
So I want to, yeah.
How do they define these ansatz for the cutoff?
Sorry? Again, say it again.
How do they define this form for the cutoff? It's an ansatz, but what do they assume?
This is an ansatz. I will show it in a while that you can use different ansatz. People have used different ansatz in the literature, but the results are more or less similar.
Okay.
I will come to that. So in fact, in this quite famous paper, that's why I quote this here. This is taken from the LQCD paper by Bali, where this is one of the first papers about inverse magnetic catalysis. So it's a LQCD paper where they got this result for this delta F is the difference between the quark condensate at the final magnetic field minus the quark condensate at zero magnetic field multiplied by some factors, okay, by some numbers, if you like. So this is basically the behavior of the quark condensate as a function of the magnetic field. So they get this straight line, but this straight region here, red. Well, if you use the Nambu-Jona-Lasinio calculation from these people, that they use you see they use a different form factor. So this is the Lorentzian form factor. They got this result, the blue line. And if you use chiral perturbation theory, you get this green. So, but you can see in this figure there is an oscillation here, and this oscillation is due to the form factor. And the other thing which is, I think is important, that up starting about 0.3 GB square, this slope is different from this one. Okay, the slope predicted by the Nambu-Jona-Lasinio model starts to be quite different from the LQCD result. So in fact, I took this sentence from this paper. We see that the chiral perturbation prediction described LQCD up to 0.1 GB square, so here, while the Polyakov Nambu-Jona-Lasinio model works quantitatively well up to 0.3 GB square, because from 0.3 GB square, this starts to depart one from each other. So as I said, I mean, this sentence was in a paper which has a lot of citation and it became very popular. So the question is it possible to avoid these oscillations? Is it possible to find another way of starting from the 3D cutoff method, get an expression for the gap equation that doesn't give rise to this oscillation? And in fact, there is. This alternative method was introduced by this paper by Deborah, Marcus, Aurora, and Progenza. what they did is to start from the pressure of the Nambu-Jona-Lasinio model in the mean field approximation, and inspired in the 3D cutoff, they first made the integral over P4. So this is the way they were thinking in the 3D regularization. So, and this is the pressure. If you have a term, which is kind of potential term plus a kinetic term. So this is the one that you have to regularize. This is in the absence of external magnetic field. This is divergent and has to be regularized, of course. Now, if you use the usual recipe, the usual prescription, when you introduce magnetic field, what you have to do is to replace P vacuum by P vacuum plus magnetic, where I have replaced this integral by a sum of Landau levels in 1, 2 directions and the integral over 3, and I replace this P1 square plus P2 square by 2K BF. So this is again divergent, of course, but they noticed using some method based on the Riemann-Hurwitz set of functions and some tricks based on dimensional regularization, that the difference between these two is finite. So they got this result. They define a P magnetic, which is the difference between these two divergent quantities, which is finite, as I said. And then they separate this pressure in the presence of a magnetic field in two pieces. One which is the magnetic part, which is finite, and the part which doesn't depend explicitly on the magnetic field, which is divergent and has to be regularized. But then I have to stress that the part that you have to regularize is not explicitly dependent on the magnetic field. So if you take the derivative with respect to the mass, you get this expression where I have already used 3D cutoff for the vacuum term. The derivative of the finite term gives you this here. Now you solve the equation for the same parameterization, and you get this red line. So the selections are completely gone, okay? And the slope, as you see, is rather different. Fine. So the question is whether this regularization method depends strongly or not in the 3D regularization of the vacuum. So I started from the 3D in the sense I first integrated over P4 and then performed this subtraction and then use 3D for the vacuum. So is it possible to get similar results for other parameterization, for other regularizations? Well, to understand that, I have to recall you the form of the quark propagator in a constant magnetic field, which is given by this expression. It has two pieces. The part which is the Schwinger, the so-called Schwinger phase, which is gauge dependent and breaks translational invariance. Which is this is the expression. But however, this expression is in path independent, so it doesn't depend on the way you go from x prime to x. So since it is independent of the path, you can choose a straight line path, which is the easiest one, and then this goes to 0. And then you have to choose a particular gauge to calculate the explicit form of the Schwinger phase, and in that Landau gauge is given by this. So this is a explicit form of the Schwinger phase when you use Landau gauge and a straight line path. And here you can clearly see that this phase is invariant on the translations in the 2 direction, but it is not in the 1 direction, which is obvious because you have an x1 here. So you have broken translational invariance when you choose your gauge. Okay, and the second part, which is this tilde, is translational and gauge invariant. And since it is translational invariant, you can Fourier transform it and introduce this S of P. So for this S of P, this S tilde of P, this F means flavor. So it's different for U and D, of course, or S. For this SP, there are at least 2 ways to write it. One is the Landau level representation, which is in here is given here. You have some exponential here and a sum over Landau levels. And these functions are the Laguerre, generalized Laguerre polynomials. And this matrix here is 1 plus minus I, comma 1, comma 2. So this is the representation in terms of Landau levels. In fact, if you use this representation and take the trace and so on, you get back this recipe that I introduced a bit by hand. The alternative way to write this S of P is the proper time representation, which was introduced by Schwinger in the 50s, where you integrate over this tau here, which is the proper time. There is still another way to write the quark propagator, which is in terms of the Ritus function. So in a way, what you do is to write this propagator, which is not diagonal in coordinate space. You transform it to a different basis, if you like, where it is diagonal. And this rotation going from X to P bar, this is the Ritus P, is performed by this matrix here. This matrix here, this delta lambda is the same as before. And these functions here are, these functions have this form, which are exponentials in the 2, 3, and 4 directions, and these parabolic functions here, which are some exponential multiplied by Hermitian or Hermite polynomials. So this is in the Landau gauge. Of course, if you use a different gauge, this will be slightly different. You will still have this plane works here, but you have a different function for P2 and for. Notice that rho is a coordinate x1 minus something that depends on magnetic field by P2. So in a way, well, you know, this is basically giving you a harmonic oscillator. And what this tells you that the center of the harmonic oscillator depends on P2. So in a way, this will allow you later to restore translation and inverse. Clearly, it is possible to go from one representation to the other, and people have shown that. For example, in these papers, you can see how one can perform all the algebra needed to go from one representation to the other. But so let's go back to proper time representation of the quark propagator using the expression I have shown 2 slides ago. You replace in the calculation of the quark condensate, and you get this expression here. So you go back to the gap equation, and the gap equation reads something like this, where this IF is integral, this integral, which is divergent, of course. So you have to regularize it. So one way is to just put the cutoff here, as we did for b equal to 0 in the proper term. This is what these people did. This paper is quite well known because this one of the first papers where they deal with the phase diagram in a strong magnetic field. But there is an alternative way, which is funny, but this was done even before. Used in the original paper by Klevansky and Lemmer, which I think they were the first to deal with strong magnetic fields in the Nambu-Jona-Lasinio model, and was used again in the famous review by Klevansky and also in a paper by Eber, Klimenko, and collaborators. And the idea is the following: you just take the IF I showed in the previous transparency. There was an BF outside here, so I put it inside, and there was the 1 over tau. I replace it by 1 over tau squared multiplied by tau. So this is exactly the same. So what you do is to sum and subtract a 1, as trivial as that. Okay, and then you are able to separate this in 2 pieces. Oh, I'm sorry. Right. A piece which is the vacuum term, which has the same form as in the absence of a magnetic field, which is divergent, and you have to regularize. And a piece which is finite depends explicitly on the magnetic field, but is convergent. Okay, this is convergent. And moreover, if you use the table of integral, for example, this expression from Grastein, you can show that this here is the same as this, and it's the same as the I1 magnetic introduced by Menezes et al. So you get exactly the same result. And now it's also nice that these people, I mean, different papers use different ways to regularize the vacuum. Here they use proper time, here they use polyvillars, and here they use 40. So in a way, we see that people have used 4 different regularizations for the vacuum, all for the model, and get the same finite piece for the magnet. So the general idea is to express any integral as a sum of a piece which is explicitly independent of the magnetic field, which is divergent, and you have to regularize, and a piece which is called a magnetic piece, which is the difference between the unregularized at finite b minus the unregularized at b equal to 0. And these two things, which are each is divergent, but the difference is finite. And you will obtain the same form of this IMAC independently of the representation of the quark propagator you use. So, on the other hand, as I said, this piece, which is a vacuum piece, has to be regularized, and you can use any of the possible methods. So, actually, when we started this, when I started to get interested in this, because I wanted to discuss the situation when the magnetic field is present, but also the color superconductivity is present. So in that case, the dispersion relation is slightly different. So it was not obvious that all these things will work, but they do. So in these 2 papers, we show that this isolation method, where you separate magnetic piece from the piece which is the one of b equals 0, can be done also for that case. And the important thing is this, that using this separation, you completely erase all these non-physical oscillations. And in this particular case, where you have actual, real Van Alphen-Dehaze oscillation, you can see that the actual oscillations are there, while these physical ones disappear. So in these papers, we decided to name this magnetic field independent regularization, in the sense that you have to regularize only the part which is not dependent explicitly on the magnetic field. But I don't know whether it is a good name. Maybe we have to think of something better. I don't know. So far I have, maybe it's confusing. I don't know. So far I have discussed regularization at midfield level. What happens beyond? So what happens if you want to regularize a loop like this? So for example, this, this was done in a series of papers by Sidney and ourselves, Sidney and collaborators, of course. Here, and it's nice that we did it in a different way, because we use different representations of the quark propagator, and we got the same result. So in fact, the finite part is independent. So the final magnetic part is independent of the representation you use for the propagator. So here they did it for the neutral pions. In this paper, we did it for the neutral and the charged pions. Here we did it for what's in Joanna Sotre and Max Scoccolla. We did it for neutral and charged SU3 pseudoscalars. There is a recent preprint by Sidney, Ricardo, William, and Timoteo, where they applied it to vector mesons, for neutral vector mesons. I have a couple of papers in preparation together with Daniel Gomez, Santiago Noguera, Juan Pablo Calomagno, where we show how this method works for the case of the neutral and also for the case of the charged vector mesons. And as I said, I mean, we use proper time, while Sidney and colleagues, they use Landau level representation. And we have also applied to the calculation of the mass of the quarks and nucleons in this other paper. So, okay, fine. This is very nice. So how can compare this result with some lattice result? Okay, so this black points here are lattice result from this paper of value. Again, this is the, remember, this is the difference of the quark condensate at finite magnetic field minus the quark condensate at zero magnetic field. So these are dots are lattice QCD, and this is the result that you get if you use different form factors. So this is a very steep form factor, so it's almost heavy side, so it's almost using sharp cutoff, if you like. You have very strong oscillators. If you don't separate the magnetic part from the equal zero part, this is what I call non-magnetic field independent regularization. However, if you separate it and you regularize only the vacuum on using this same function, you get very smooth behavior, which is quite close to the lattice. So now if you use a different form factor, so 5 is Lorentzian with n equal 5. So this is in fact what we was shown in the paper by Bali that I've shown before. So the only thing I extended here the scale. So see, this is the result of Lord 5, and this is the result of lattice. You see the oscillations, and you see that above point 3.4, there's a big departure from results. While if you only regularize the vacuum, then you get this smooth behavior.
Sorry, Norberto.
The band, I'm sorry, I didn't explain what the band is. The band corresponds to different parametrizations corresponding to different quark condensates.
Norberto,
I'm sorry.
what are the two blue lines? I mean, the traced one and the full line. You have the lattice, and then you have.
This is what I was trying to say. They correspond. It's easy to see it here. They correspond to different parametrizations of the model. So as I said, you fix f pi, you fix m pi, but you have some freedom in the condensate.
Okay.
So in order to really understand whether this is really dependent on the parameterization, we use different parameterizations that give rise to condensate in this range, which is
okay. So this is like the minimum value of the condensate and the maximum value.
Right.
Okay.
Fine. So in a way, you can find some parameterization where your results are just on top of the lattice, but you know, this doesn't mean much because there is some freedom. And here for the Gaussian, which is very smooth, you see the oscillations almost disappear for the Gaussian, but still the slope is very bad, I would say. It's not so good. Okay. Moreover, I have to say that the Gaussian is a bit tricky because with this very soft regulator, it's very hard to fit m pi, f pi, and the condensate. So some people have used the Gaussian regulator. However, when you look at the f pi and m pi, they get it, they're completely crazy. So, fine. So you can get something smooth, but the price you pay is your parameters are kind of funny in the sense that they don't reproduce standard physics or pion physics. Good. Now, these are results for different ways to regularize the vacuum within the magnetic field independent regularization. So here I have already separated the vacuum from the magnetic part. For the magnetic part, I use the finite value, which is given by expressions I showed before, but I choose different ways to regularize the vacuum. And this is what you get. So there are more trends are rather similar. Somehow I would say that this is better, but it's not a big difference. Probably this is quite away from the lattice results. also, again, I have to stress that proper time tends to give very small quark masses. Finally, I think this is also interesting because I think it is clear by now that to use the form factor regulators without separating vacuum from magnetic is not good. However, you can still use other regularization methods like proper time without separating and separating. You see, proper time doesn't make such a big difference. So you can implement magnetic field independent regularization also in these cases. However, the results are not so different as before. So basically the form factor is still good, but the others, they're not so bad, okay? In particular, you see Pauli-Villar's more or less the lattice numbers. I have to stress once more, however, that the Pauli-Villar's works okay. However, the mass is rather low. So it's 300 MeV, the typical quark mass. So this means that, for example, if you want to use this model for rho, then you might be in trouble because rho will be in the continuum. Okay, so now I change the subject. Treatment of a charge mesons.
Norberto, a question?
Yes, please, Christian.
Well, it seems that the winner is the 3D regularization. Huh?
Yeah, this is the one I like, yes.
But do you have the number of the chiral condensate that fits with this regularization, the lattice result?
Yeah, I think it's the one that gives you a mass of 350 MeV. I don't remember exactly the condensate, but it's around 240, I think. Okay. So it's reasonable. Yes, sir. Okay. However, I prefer to use 3D, but okay. From this figure, you cannot really conclude that this is much, much better than the others. Okay, probably this is the worst, but the others are not so bad either. Okay. Anyway, so
may I interrupt you?
Sure.
Just because it's perhaps this is the correct place during your presentation, and because I may forget at the end, but I believe that the partial conclusion from what you're saying is that you cannot mix vacuum with magnetic field effects. And as a general observation, I guess one could have expected this a priori, in the sense that if you think of the analogy with a thermal system, it's true that you cannot mix vacuum with temperature or density for that matter. And the reason, again, a posteriori if you wish, but at the same time, I think that it could have been expected, is that if you look at this, the scales, the length scales associated with the magnetic field, which is the inverse of the square root of the field strength, or for the temperature case, the inverse of the temperature, these length scales are never as small as the inverse of the ultraviolet scale. So there is no way you can mix them. The ultraviolet scale will always be far away separated, no matter how strong the magnetic field is, no matter how large the temperature or the density are. Mm-hmm. So these are two very different scales, and therefore the physics has to be very different, and therefore you can expect that vacuum is separated from medium effects. And when I say medium, I can think of a magnetized medium or a thermal medium or whatever. So but this is clearer. I mean, I can see that, as you mentioned, the Nambu-Jona-Lasinio model has the model itself contains a vacuum regularization. It's a non-renormalizable theory. But you can see this in renormalizable theories, even effective theories. And I've been trying to portray for quite a long time already that the stigma model is one of them, which is very handy. And there you can clearly see that when you do magnetic field calculations, what you do is you separate the vacuum cleanly, and everything that is vacuum, including the ultraviolet scale, goes into the error normalization of whatever observable you're doing, and the rest is just purely magnetic field effect or medium effect, so to speak. So I guess in general you're right. It's only a matter of taste in this case, which procedure you use to fix the vacuum parameters. And as you say, that as you see here in the plot you're showing, the plots you're showing, it's like I mean there's a choice, so to speak. Mm-hmm. And there are better ones than others. I suppose that for other observables it may be better some or the other. Yeah. But in my opinion, this is the intrinsic physics that is, and I agree completely with your analysis.
Yeah, actually, as you know, it is well known that, for example, in the Nambu-Jona-Lasinio model, you usually cut off the non-thermal part, but the thermal part you don't introduce any cutoff because it's finite by itself. So you don't have to introduce a cutoff. But in principle, you could say, well, if I put a cutoff in the vacuum, why not to put a cutoff everywhere? However, if you put a cutoff in the thermal parts, you're not okay. And the same happens with the anomaly, the pi 0 to 2 gamma. The pi 0 to 2 gamma, there was also a long discussion, I mean, years ago already, that this loop, the pi 0 to 2 gamma, the quark in the loop, you might have any momentum. But if you, so in principle, you say, well, if I cut the momentum at the cutoff lambda, I have to cut off also in the triangle. But if you cut the triangle, you get the anomaly completely wrong. So you don't have to, in a way, you don't have to cut those things which are finite.
Or put it in another way, you have to, as you said, separate vacuum. It doesn't matter what process you're talking about. Separate. Yeah. And then you do the rest with the other medium.
Yeah, but you see, I want to mention something that in this part, this is you have Landau level, lowest Landau level dominates. You see what I'm saying?
No. But it goes. Maybe we should postpone it for the later.
Yeah. Because this is something I don't understand.
One thing, even if you work with a single Landau level, which you may think dominates at large magnetic fields, which is the case of the lowest Landau level.
Yeah, but then
neither the lowest Landau level nor any single level contains all of the vacuum. So it's a partial contribution from each single level, and then you have to take care of everything in order to separate cleanly the vacuum. That's my point.
I completely agree. But then, okay, let's discuss this later. Because I think this topic is also interesting. Is that treatment of the charge, the mesons? I think it's interesting because there have been quite some confusion about this topic. So in the Nambu-Jona-Lasinio model, the contribution of the pions to the chiral action is given by a term like this. So this is the inverse propagator of the pion field, if you like. So for neutral pions, this loop here is given by this. Now you replace the form of the propagator in the magnetic field, which I said is given by the phase and the part which is translational invariant. Now you replace here, and you note that here it goes from x to x prime, and here from x prime to x, and they correspond to the same flavor. So, of course, it's quite obvious that if you interchange x prime with x, this will get a minus sign, and they will cancel the other one. So, in the case of the neutral pions, the Schwinger phase is cancelled. And therefore, this loop here, this polarization function, is translational invariant. And since it is translational invariant, you can diagonalize it, performing the transformation from coordinate space to momentum space, so it's the usual Fourier transform. And in this new basis, this matrix, if you like, is diagonal. And since it is diagonal, you can invert it. Okay? And then you get the usual equation for the pi zero mass, which is the same, I mean, it's similar, if you like, to the equation that you got at b equal to 0. Of course, it is not the same because this invariant part of the propagator is different when you have a finite magnetic field. So that's why this regulated part will be different from the b equal to 0 case. By the way, this is divergent and has to be regularized, and you can use magnetic field independence for this. Now, what happens with the charged pion? For the charged pions, for example, for the pi minus, this is the loop, this is the polarization function. Again, you have the U propagator, I'm sorry, the U propagator, the D quark propagator, and the factors I gamma phi. So when you replace these propagators by the explicit form, which contains the Schwinger phase, so you get these two Schwinger phases here, and this part, which is translation invariant. However, in this case, the quarks are different, so the Schwinger phases do not cancel. And since they do not cancel, you cannot diagonalize this going to momentum space, which is pretty obvious. So you cannot use a Fourier transformation to diagonalize this matrix, if you like. So you have to use a different basis. And the basis you have to use is given by these functions f, which are the solutions of the Klein-Gordon equation of a point-like charge pion in a constant magnetic field. In a particular gauge, Landau gauge, for example, but what I show here is the Landau gauge, but this can be also done in the symmetric gauge or in any other gauge. So you see, instead of the usual momentum, for momentum, you get this kind of, I would like to call it Ritus for momentum, which has an index, an integer k, which labels the Landau level, the Q2, Q3, and Q4. However, you have to recall that this Q2, although it's conserved, so it can be used to label the wave function, it is not physical. Okay? I will come to that in a minute. So it's not a physical quantum number. And it's so that if you use a different gauge, this Q2 will not even appear. So for example, if you use the symmetric gauge, there is no Q2. Now, this F has this explicit form. So you have plane waves in the 2 to 4 direction. And again, you have kind of a harmonic oscillator in the x1 direction. And this oscillator is centered around, well, this factor multiplied by P2. So the center of the oscillation depends on P2. Of course, you can choose any value of P2. This means that you can choose any center, as it should, because the whole system is translation invariant. So in a way, this F is similar to the Ritus function for the spin 1/2 particles. So that's why I like to call this Ritus function, but this actually is not a Ritus function. This is for the pseudo-scalar Ritus functions that are introduced for spin 1/2 particles. Now, you replace that and you get this, where this function here now is in principle not diagonal. You see, I mean, there's a Q and Q prime. So remember that Q bar is given by this. So in principle it's non-diagonal and is given by this expression here, long. However, after a long but straightforward calculation of, I don't know, many pages, you can show this is diagonal. So in fact, when you make a rotation, if you like, from the coordinate space to this Ritus space, you get your polarization function diagonal. Well, once you get it diagonal, this pi square is kind of, well, at the end I will put pi square equal to minus mass square, because this is given by this. And this is diversion, and again, it has to be regularized. We use the magnetic field independent regularization. And once it is diagonalized, you can calculate the mass of the pion, the charged pion, using this equation. And note that you will get a different mass for different Landau levels. So one usually look for the lowest energy state, and this corresponds to k equal to 0 and q equal to 3. So because I put 0 here and 0 here, and this is what defines the lowest energy, the lowest possible energy of the pion in the magnetic field, which is given by the square root of m squared. This is the m that you obtain from this, plus this EV. Okay. Now, important thing, you cannot put a pi minus at rest in a magnetic field. To start with, there is no Q1 in the Landau gauge, so you cannot set Q1 equal to 0 because there is no Q1. Second, there is a Q2, although it's conserved, it's not a gauge-independent quantity. So this means that if I use a different gauge, Q2 will take a different value. So it doesn't make sense to set that it's physical to put Q2 equal to 0. Doesn't mean anything. And why? Well, I think my understanding that you always have some kind of 0-point motion in the 1-2 direction. Because, well, this is the way I like to think, but maybe it's not fully correct, and maybe we can discuss this. Because you have a kind of harmonic oscillator in the one direction. The best you can do is to put this harmonic oscillator in the lowest level. But you cannot simultaneously fix X1 and P1. So you always have some kind of motion, if you like. In fact, this is always there. Also for fermions. The fact that for fermions, this is just cancelled by the spin contribution. So for fermions, the lowest energy is just the mass. But in principle, it's over there. So I come to the conclusion. There are different methods that have been used in the literature to regularize the Nambu-Jona-Lasinio under electromagnetic fields. The form factor regularization generates some physical oscillations. In principle, you can try to get them small by using a very soft regulator. However, if you use a very soft regulator, you have a problem with the parameterization. On the other hand, the magnetic field independent regularization avoids these problems. And in this kind of regularizing the model, you separate the vacuum from the magnetic term. And the magnetic is finite, and you have only to regularize the vacuum piece. This method have been used in different calculation at midfield level, at final temperature, chemical potential, models with pairing, and also for a meson polarization function. So in a way, we have proven that this works. Vector polarization functions, pion polarization functions, etc. Axial. There have been a couple of extensions, or one by Sidney, Ricardo, and William. They introduced the so-called set magnetic field independent regularization. The set comes from the Riemann zeta function, which is in fact equivalent to the magnetic field independent regularization, but they claim they have some numerical advantages. So what I mean is that if you use this alternative way of introducing the regularization, you get exactly the same result for the things I have shown. And recently, there have been a couple of papers by Sidney again and collaborators where they introduced the vacuum magnetic subtraction, which is the same as the magnetic field independent regularization for fixed B. So in a way, what I'm saying is that once you have the gap equation, you can go back to the pressure. For that, you have to integrate. But when you integrate, you might have some unknown constant, which doesn't depend on M, but might depend on the magnetic field. So, in their way of proceeding, they take into account this extra term, which they show it is important for the calculation of the magnetization, because the magnetization is a derivative with respect to the magnetic field. So it's important to keep that constant too. Concerning the calculation of the charge pion properties, Schwinger phases are important. They have to take into account, you cannot neglect them. And what I have shown for the 2-point function is true also for higher loops. And its gauge non-invariance ensures the gauge invariance of the action. So it is important that the Schwinger phase is non-gauge invariant because it makes the whole action gauge invariant. I can show this in a while if you like. Polarization functions have to be correctly diagonalized using the proper basis, which are given by the eigenfunctions of the associated point, like meson equation in a magnetic field. If you are dealing with pseudoscalar, this would be the Klein-Gordon. If you are dealing with rho meson, it would be a Proca equation and so on. Charge particles cannot put at rest. You cannot set Q vector equal to 0. But to remember that the components of the linear momentum, which are perpendicular to magnetic field, are gauge-dependent quantities, and therefore they're not physical. So it doesn't mean anything to set Q1 equal to 2 equal to 0. So that's the end. Some extra transparencies we want to discuss more.
Thank you, Norberto. So if you want to open the microphone to thank our speaker. Oh, I have a couple of raised hands here.
Clapping.
Alejandro.
I hope Alisa have been.
Alejandro, you're back.
Yes, I am here. Thank you, Norberto. This was a wonderful talk, very, very clear and illustrative. And I already had some comment on the first part of your talk, but I wanted to comment and ask you also about this second part, which is hereby summarized in this slide. And I have some problem with this interpretation that you have mentioned. Maybe you can clarify it. It is perhaps just my own personal ignorance. But you see, when you have a loop with charged particles, which, as you said, the sum of the charges do not add up to 0, then what you've shown is that there is a phase in the loop. Right? But then this usually happens when outside the loop, you have also charged particles that are coming in. And therefore, their quantum description has to be also subject to the fact that when they propagate, they change their phase. In such a way that when you see, this is the way I think of it, I may be wrong, but if you come up with a particle that has some charge, it breaks up into a couple of particles in the loop, one of them having a charge different from the other one, and then it reconstitutes and keeps moving, then the changes in phase in the loop have to be somehow related to the changing phase of the moving outside particle, so to call it. So it is not surprising that the loop is gauge dependent. However, if you take into account the gauge in the phase of the external particle, then you should have a matrix element which is gauge independent. Maybe I'm missing something, but
no. It's so obvious. But people keep using plane waves for charged particles in the magnetic field, for external particles, legs of the particles in the magnetic field. I mean, full of wave precision.
No, that's the point. Even if you use plane waves, you can
No, you cannot use a pion.
Sure, because
doesn't have a wave function which is a plane wave.
No, wait. If you have the external particle propagating for long distances, of course, it's not that way. But the particle doesn't break up into another particle from the distant past. It breaks up into a couple of particles in a very localized place.
It's not the point whether it is the pair is created. The point is that the external particle is already moving an external field.
That's what I'm saying.
The external particles, forget about any loop. Just you have a pion, charged pion moving in an external field. Okay? The corresponding field is not a plane wave.
True. But when it breaks into a couple of particles, the process is localized.
Yeah, sure. That's fine. That's fine. But it creates this.
When that happens, then the phase that the particle came in with has to translate into the phases of the loop particles in such a way that at those points, which are localized, gauge invariance has to be satisfied. There's no other way.
Completely agree. Yeah, what I'm saying is that
you forget about asymptotic propagation to describe that process. That's the point. And for that matter, then you can use plane waves for the point-like process when the particle breaks up.
You can't.
Well, I can show you, but
I mean, look. What I'm saying is that you have to have this phase. I mean, the field itself.
When you enter, there is no way that the particle that breaks up into a loop particle knows that it's coming from some weird trajectory which is bent by the magnetic field.
Yes.
I mean, at the point when it breaks up into the loop particles, it's just coming as if it was.
But it carries a phase that just cancel the phases of the loop.
In a very small.
No. Everything happens at one point. At one point. Everything happens at one single point.
Well, okay. We can perhaps later discuss this, but this is, I think, at the core of some at least intuitive way of understanding this process. Okay, thank you.
Christian?
Thank you, Norberto. Very nice talk and illustrative. I would like to ask you about what happens with some missing formalism here. That is the expansion in powers of the magnetic field, which is often used. What happened with all these claims, for example, in your conclusions that charged particles cannot be put at rest?
Yeah, I mean, well, how to say? I mean, even if the magnetic field is very small, I mean, classically, it describes a circle. It's not a straight line.
What sort of?
Okay, you might say that the radius is very large, and I would agree, but then you have to be careful how you expand it in this radius.
For instance,
which is a magnetic field.
It's less than the square mass.
Yeah, what I'm saying is that once you put a magnetic field, your wave function changes, and it's no longer a plane wave. It's basically some exponential, some Gaussian multiplied by some Hermite function. So maybe you can expand this in a plane wave too. I don't know. It's complicated.
Yeah, it's not so simple to get to the result. At least at the propagator level, you can go to one to another.
Yeah, sure.
So it means that if you expand a magnetic field, maybe it can be set as a.
Yeah, maybe we'll have to think about how to expand the Schwinger phase.
maybe can be described in terms of sum of plane waves or not? In the case of an expansion.
Maybe perturbatively, I don't know. I don't know. It's like trying to use in a harmonic oscillator to use plane waves to describe some harmonic oscillator states.
Okay.
Maybe if the field is small, you can do it. I don't know.
And the way
I always think in strong magnetic fields. So when B is not small. So.
Yeah, and I have another question. So the only way, for instance, in this case, in Nambu-Jona-Lasinio to extract the masses of the charged pions must be in the Ritus formalism, isn't it?
In the
Ritus?
Ah, yes. Well, I mean, I'm just saying that you have to use the wave functions of the corresponding point-like particle in a magnetic field. This is what you do, actually, always. I mean, in the absence of a magnetic field, what you do is you expand in solutions with of the triangular equation in the absence of magnetic field, which are the plane waves. That's why you expand in plane waves. But when you have a magnetic field, you have to expand in the eigenfunctions of the triangular equation in a magnetic field. This is the only thing I'm saying.
Yeah, but if I understood, I don't know if I understood well, but what you do is to redefine the momentum dependent pion field according to the F function.
I'm just using the quantum numbers that describe let's say a point-like particle in a magnetic field, which are not the same as the momentum, the usual Fourier momentum. Right.
Yeah. Ah, okay. This is this.
Yeah, you have to use these alternative quantum numbers.
Yeah.
If one uses well, okay, fine. That's down.
Okay. Thank you.
Jose Luis?
Hi, sure. Hi, Professor Norberto. I just have a question. In the procedure that you show us, you use the Landau gauge in order to find this diagonal, in order to find this matrix to diagonalize the expressions for in order to compute the Schwinger phase. Yes, that's slide. And in the case of course, you can choose another gauge, for example, the symmetric. And in that case, you have to use the eigenfunctions that you obtain from the solutions of the Klein-Gordon equation using the symmetric gauge, as far as I understand. My question is there a way to do this procedure using an arbitrary gauge that give us, for example, the physical case of a magnetic field that points in the z direction uniformly and constant in time?
Yeah, you can do it in any gauge. The problem is at some point you have to fix the gauge to perform the calculations. But from this function f, you can gauge transform it to any gauge. Because you know how it transforms. It transforms to exponential minus lambda x, where lambda is the function, the scalar function that makes the gauge transformation. So you can start from this one and transform it to any other gauge. And the same you cannot do it starting from the symmetric gauge. We have a paper also using the symmetric gauge. And you can start from those functions and transform them to any other gauge, if you like.
Yes. Yeah, my point, the point of the question is because if we do this kind of transformations, we have an arbitrary function that relates two different gauges, two different choices for the gauge.
Yeah.
And in the case of the polarization function, we show that this part that depends on the Schwinger phases is independent of this arbitrary function. That we are done. We show that this kind of procedure give us a polarization function that is gauge independent, I guess.
No, you can't. I mean, I was showing here. Well, you look at this expression. So this field depends on the gauge. So transform like this under gauge transformations. So in order to have a gauge invariant action, this has to be also gauge variant. So it has to depend on the gauge. You have to get the phase which cancels the phase that comes here. And this is because this is non-local. Depends on two different coordinates. So if this is local, then this x prime is equal to x, then the phase coming from here will cancel the phase coming here from here. But this is a two-point function. This is non-local. So you have to make some parallel transport, if you like. And this is what the Schwinger phase does. It's basically a parallel transport.
Okay, yeah, I can see.
So it has to be gauge variant. So it has to depend on the gauge.
Sure. Okay.
Otherwise,
Thank you.
You don't get a gauge invariant action.
Okay. Yeah.
Okay. Gastão?
Yeah, Norberto.
Right.
And I have seen a lot of work in this Nambu-Jona-Lasinio and this non-local Nambu-Jona-Lasinio, and also in linear sigma model. These are all, say, schematic models for dynamical chiral symmetry breaking. Right? Have you seen other kinds of approach? You have chiral perturbation theory, but I guess that is valid for very low magnetic fields, right? So these people make a lot of noise with Dyson-Schwinger equations for calculating spectrum and all that, but I have seen not much work on magnetic fields. Okay. What is the situation there?
You have not seen much because it is very difficult.
It's very difficult.
Yeah, because you have all these phases everywhere.
Yeah. But so I think the question is actually how reliable are all these things that we are doing? I'm including myself because I do this too, right? So
okay, fine.
Okay, we fit. Okay, we have some lattice data, and then we fit them, and do we have understanding of probably not, right? So we change coupling constants, we mock up things here and there.
I agree. I mean that. Well, how to say?
We do
one possibility is to try to define your model, perform the calculation, and then compare with lattice.
Yeah, but I want more than that, right? I think we need more. We have to understand what is happening.
Yeah, but first you have to get a model that works without fitting it to the lattice data. That it works by itself. You mean what? You understand what I mean? That.
Yeah, if you have a crappy model, so please don't start doing anything.
But you can always play around with the parameters and try to fit invent numbers or functions, and then you fit lattice QCD. And fine, but it's completely arbitrary. But what I mean is, if you fix a model, perform the calculation, and it compares with lattice and it works, then you can understand something from the model. The other way, don't use the lattice data as input, is what I mean. Because otherwise, of course, well, okay, maybe sometimes it's useful because you say, well, if I use this function, but then you have to understand why this function and not the other one. No?
Okay.
Okay.
So, yeah, I want to leave the Nambu-Jona-Lasinio and go to someone else, but so you guys don't have any suggestion where should I go, right? What direction?
Oh, yeah, go to QCD, yes.
Where?
Sorry?
QCD.
Yeah, I know, but Norberto tells me don't go there. It's too difficult.
No.
Come on, Gaston.
No.
But Gaston, what you're suggesting is that we should explore more models or more, not models, but approaches.
Or have some
there is some work on Schwinger Dyson done for a strong magnetic field. Considering only like lowest Landau level, but yeah, for any value of field, it's more complicated.
As a community, probably here we should probably focus in brainstorming some new initiatives and things like that. Right? I have not, Norberto, probably you are familiar with this Coulomb gauge QCD, right? This is.
Yeah, I know the name, but I didn't work with this, and I don't know much. I mean, I am not an expert in this.
I thought you were. Anyway, I would like to leave a little bit the Nambu-Jona-Lasinio, the linear sigma model. I don't know. Does it work, Alejandro?
Yeah, it does. Well, it depends what you want to describe, but the point here is that, for instance, what Norberto is showing us has to do with the behavior of the condensate, which is an order parameter of the chiral transition as a function of the magnetic field. If you add the temperature on top of that, then what you're doing is to describe the effects of the magnetic field on the chiral symmetry breaking. And this is the essence of these chiral models. Nambu-Jona-Lasinio is one of them.
I know, but in the linear sigma model, does it work there? Does it?
Yeah, that's what I'm saying. And so the point is that the linear sigma model tells you already, being renormalizable, that you separate vacuum plus thermomagnetic contributions. You can even show that you separate cleanly the magnetic effects from the thermomagnetic effects, so there is only pure magnetic effects, and then you can study. Of course, it is a model that you need to fix the couplings, but the overall picture seems to be right in the chiral symmetry restoration description. That is the point. But I think you're right. One has already accumulated a lot of experience in these models to go on into the next step, not necessarily into the Schwinger Dyson, which is already been explored, of course, by a lot of people. But what I think that it's not being explored a lot is perturbative QCD. So I think I totally agree with you, Gaston, that we as a community should try to provide some guidance as for what is the question that can lead us to a clearer and deeper understanding. I agree. But one of the things that I think that the community hasn't explored so far so much is perturbative QCD, which is not easy, but it's not Schwinger Dyson. That's what I'm saying. Where you mock up a lot of things. There it's a fundamental theory, and then you.
Hey, thank you.
Yeah, I mean, I would also say that I think as a community we should, I don't know, focus on making some kind of, list of observables we can calculate with that, because in the end we have to compare with, experimental data. So there a few quantities that we can calculate as a function of centrality, but we are missing the end of this. I mean, we cannot predict from where we are now. We cannot do predictions yet. So we have to work on what kind of. So if we're calculating, I don't know, mass spectra, well, can we compare this with, I don't know, mass spectra from the experiment or not? I mean, I think we have to discuss that. Not only change model or whatever, but to see what we can really compare with data here. Ricardo?
I agree with the proposal to try to think in new approaches. But my question for all of you is, we can put the fault in the approximation. We just do mean field. It's not the time to try to put our hands and try to do something beyond mean field. I guess this can be one way to do something different.
Yeah, but go beyond mean field in Nambu-Jona-Lasinio, I think is kind of too much.
No, that's what I think Ricardo is saying, that you use other models, which I keep coming back to the linear sigma model because it's easier, but there you can go beyond mean field. That's the point.
Usually we do the simple approximation because it's easy. But we have problems. We have few degrees of freedom. But I guess some approach beyond mean field can help something.
Yeah, but what can be calculated in QCD itself?
This is it's much more difficult. I guess
Yeah, I know. Of course it is.
I guess beyond mean field will be
of course it is, but we've been doing this simple thing for many years now, and I totally agree that now we have to face the more difficult thing and spend the next 10 years doing that if it's necessary, but it's time for doing that. So.
It is for young people.
Well, but anyway, any more questions about the talk about regularization methods that Norberto has presented to us? So if not, let's thank Norberto again. And I suggest that we have a meeting to discuss like future strategies to go beyond the point we now, I totally agree it's necessary. Maybe we can meet to discuss only that. What do you think?
Well, actually, I have been with Marcelo Leve, been working with QCD sum rules.
Yeah.
We are able to obtain some parameters. This is a good way to compare it. But the problem with QCD sum rules is that it needs some inputs, magnetic field dependent inputs. So it's not like, for example, Nambu-Jona-Lasinio, that you fix the mass and the ion decay constant at vacuum, and then it predicts a lot of stuff. But for example, getting as I input, putting the chiral condensate of lattice chiral condensates, we are able to reproduce a lot of other parameters. This is an alternative way. I mean,
yeah, for example, if QCD sum rules, we can predict mass spectrum. Yeah. And then this is something we can compare with experiment. So think about something like, I don't know, mass spectra as a function of centrality, assuming that the value of magnetic field change with centrality is something that can be done. And now you have developed that, because a few years ago, it was really hard to work with some rules in a magnetic field, but now our colleagues have reached a point where it's more treatable. So yeah. Okay, so I can organize another meeting to discuss like future strategies if you're up to it. I will stop recording now.